In this lesson, we're going to look at one of the most difficult parts of metallurgy, insofar as a non-metallurgist is concerned. And we're going to try to come to grips with equilibrium diagrams and solidification. There's a lot of language that's associated with this that's difficult. And to some, the concepts are supposed to be difficult. I think that the concepts are rather simple myself, and I propose to share that simplicity with you. Actually, what we're going to be interested in is what happens when we mix two metals together, what changes insofar as their characteristics are concerned. And to understand this, you can think in an analog method about something else. Actually, this is very closely associated with the culinary arts. If you know something about cooking or making ice cream, then you understand a lot about what I'm about to tell you. However, we will be interested in finding out the temperature behavior of a material as we take it through its melting point. If we had a pot of metal, let's suppose a pot of lead, and we wanted to solidify it, what we do is to provide a heat source, get it molten, and if we want to know its behavior, let's say its melting point, its unique melting point, then we want to cool it at some constant rate and keep track of the temperature of the pot of metal. And we do this just by sticking in a thermocouple in the pot of molten metal or any temperature measuring device. And what we will find out if we keep track of the temperature as a function of time in an ideal case is something that looks like this curve. Actually, what we do is we plot the temperature or read the temperature at intervals of time starting at temperature A, or point A in time, and that's the temperature. As we move in time, then the temperature begins to drop, continues to drop until it gets to point B. At point B, the temperature remains constant from B to E. Over that period of time, it's constant. And the reason it's constant is because the metal has to get rid of its latent heat of crystallization, or its latent heat of fusion. Actually, in a pure metal, the latent heat of fusion and latent heat of crystallization are identical. You just get the latent heat of fusion coming out exothermically on solidification and having to be absorbed, that extra amount of energy, on heating up or on melting the material. After it gets to point E, the material continues to cool in the solid state. Now this has a lesson for us already. Most people visualize, let's say, a piece of metal, a metallic material, an alloy, as an entity all by itself. One thing. But this curve tells us already we have a mixture of things. So between B and E, we don't have one thing. It may be a pot of lead, maybe a pot of copper, some singularity that way. But in that, we have solid copper and liquid copper, or solid lead and liquid lead, or a mixture of a liquid and a solid. When we get to E, everything is now solid, and we just cool the material off again. Well, this is an ideal cooling curve. And actually, we'd like to see what a real cooling curve looks like, and we see that in the next slide. In this slide, we do identically the same thing. Put the alloy in a pot, heat it up to, or put the metal in a pot, heat it up to position A, start cool it off. It cools off along this curve in time. Finally gets to B. Now that is the melting point. That is the solidification temperature, but it doesn't stop there. It continues. It goes on down to point C. And so what we have done is supercool the liquid. We have a liquid existing at C that's not supposed to be there. It can't exist below D. If we continue the measurement in time, the temperature begins to go up. That's because we're giving up the latent heat of fusion, or the latent heat of crystallization in this case, and it takes the environment around it up to a higher temperature, brings it all back up to the elevated temperature of D, and it'll stay at that point from D through E. And now we need to know something about supercooling or why that happened, but we only have to notice it now that at E, it's in the solid state, and it cools off in accordance with its specific heat. Now that's for pure material. I want you to pay attention to the fact that this gap between BD and C is not too great. If we took an impure material if we looked at an impure material now, you find that this gap is much bigger. And that says that, I don't mean an impure material, I mean a pure material now. In this pure material, absolutely pure material, the material has no nuclei in it that can get solidification started, so you can cool it to a lower temperature. You might be surprised to find out that in pure metals, people like Turnbull and Seck have found out that they can supercool materials as much as 50 to 100 degrees. So there's a tremendous amount of supercooling that can be done on some alloys. But always it heats back up to this particular temperature, the solidification temperature, and we have the two-phase mixture that exists until it solidifies again. Now notice that this particular material has a supercooling represented by that much on the diagram, and if we took the same metal but we put an impurity in it, you'd find that it wouldn't be supercooled as much. That's because we have foreign particles in there that will serve as nuclei to start the solidification earlier in its life. And so it looks exactly like the curve before, except the degree of supercooling is less. Well,
when that curve goes down, it means that you, on the outside, the temperature is lower than the metal, right? But you cool it down.
The temperature on the outside is always, the question is...
Always lower.
The question is the temperature on the outside of the crucible lower?
Is that lower than metal?
It's always lower than the metal, because that's what's cooling off the pot.
Okay, when it goes up, does that mean that the metal actually gets the heat from outside?
No. It gets it from inside. Now, let me see if I can express it a little better for you. Let's suppose we look at atoms in the metal. The atoms in the metal are running around, chasing around at high temperature. They're diffusing or floating all over the place, right, at high temperature. It's liquid. And you'd keep dropping the temperature, and finally they get locked into a position that's the crystal position, except they're in a high degree of vibration around that point. And they've got to give up all that vibrational energy and become solid, right? Fixed, one distance between the two atoms in the solid state at that temperature. Now that vibrational energy that it gives up is inside the pot. It's right there, all right? But there was just a little bit of metal that was solidifying. It's the nucleus. It's a mixture of solid and liquid. So that solid metal gives up that extra heat to the liquid metal that surrounds it. And so the temperature of the pot as a whole goes up. Got the picture? All right. Well, if we look at the next slide, we find out that we now have a little problem in our words that we use. Most people have a problem with the word solution. They think of solutions as liquid solutions. They've always seen solutions that, let's say, are one liquid, you know, a solution of, say, salt and water. It's just one solution. It's liquid. But we can have a liquid that will not dissolve another liquid, and we can have a mixture of those two liquids. So we have liquid A and liquid B together. And we want to describe those two liquids without identifying them, and we call them phases. We say we have two phases, phase A and phase B. If you look at this slide again, you'll find out now that we have a liquid on this side and a liquid on that side. If we take a temperature level, and let's say the temperature is right through here, at that temperature I'm going to have a liquid of this composition and a liquid of that composition mixed. But everything is going to be liquid. Now you know this already. You know you can take oil and water and they don't mix, right? You shake them up and you could get a very, very fine dispersion that would stay dispersed for a long time. And you call that an emulsion. Two liquids that'll stay together. So inside of this particular liquid mass now we have a mixture of two things, and we call them phases. And I identify a phase as a mechanically separable or optically identifiable part of a system. Can we separate these two things mechanically? Suppose it's oil and water. Suppose it is an emulsion. All I got to do is put it in a centrifuge, and I can take the butter fat off or whatever you want to do out of the milk, or separate the oil from the water. Well, what does this look like in metallic systems? It looks the same way, and we can have liquids that won't mix. But in this particular case, I have two solids now. I have a solid over on this side, which is copper, and a solid over on this side, which is silver. And if I mix these two together, not in the liquid state, but in the solid state, I find, if I do this, I find that I have a mixture of, let's say, the copper alloy that would be on this side and the silver alloy that would be on that side. They mix together to give me a region. It's a two-phase region right in the center. And so we don't have just liquid solutions. We have solid solutions. It's actually possible to have a solid solution. When we do this, we are going to have a material which is now optically identifiable or mechanically separable, not mechanically separable, but optically identifiable. There's just one thing, So the alpha phase and the beta phase each will be one thing. We'll have a mixture of those two phases, and we can identify them. Well, to understand where we go from there, we run into the thing that gives most metallurgists and most people in general, when they understand this thing, a problem. And we run into something called the inverse lever rule. Now I want to try to explain this to you by drawing you a little map. I don't know much about the terrain here, but I do know we're at Livermore, right? And I do know that I'm staying in a place called Pleasanton. And let's suppose that right here is Pleasanton. This is Pleasanton. I'll just put a P there. And over here I'm going to put a L for Livermore. And we're here. And I take this gentleman and I give him my car and I said, I want you to run over to Pleasanton for me. And he drives some distance from here to here and his car breaks down right there. And he gets me on the telephone and he says, my car broke down. And I said, where are you? And his response would be something like, I'm 3/4 of the way to Pleasanton. That's where he was going, right? How did he measure 3/4? He measured the length of the line from here to here. Let's call that A. And he measured the length of the line from here to here. And he calls that B. And he says that A over B is equal to 0.75, or 3/4, right? Now we call that the inverse lever rule. And although it's that simple, then we'll have a problem with it, even today. But it says if we have a position on a line and we want to know what the proponents of that, what proportionate parts of that are P and L, if I just drew that and say that's a metal called P and a metal called L, and I want to find out how much of L I have if I'm right there, then what I really have is P, let's call this X right here, I have PX over PL times 100. That's the percentage. I measure on the opposite side of L, right? That's the inverse lever rule. Well, knowing that, and knowing how to run a cooling curve, we can construct percentage diagrams for any combination of metals that we want. In the next slide, you'll see that what we have done here now is put together two materials, two metals. And these two metals are copper and nickel. And we get a phase diagram. But in that phase diagram, we have just two lines that describe the entire system. That is to say, on top, we have a line that goes like this, which we refer to as the liquidus. Everything above that line is a liquid. And then we have a line below, which is this one, and we call that the solidus. And everything below that line is a solid.